Okay, guys, let's get started. 10:06, the recording is started as well. So this is the group where I record all lectures. It will be available for you guys at some point as soon as all the access and everything is sorted out, which should be by end of this week, latest. Okay, so anyway, I think the last time we might have covered this very quickly, irrational numbers and real numbers. Do you guys remember if we did any of these examples just yet? Okay, all right, so let's start here today. Irrational numbers and real numbers. We've defined a lot of things before this. Let's just wait for that.
So the committee is currently running ticket sales for the beach day, which is taking place on the 4th of March, which is this coming Tuesday. Tickets are being sold in the Student Experience office at only 80 Rand. With your 80 Rand, you get free transport to DU as the venue, a free meal, and a free drink. Tickets are limited, so make sure you get your ticket to avoid disappointment.
Okay, so where was I? Irrational numbers, thank you. Irrational numbers and real numbers. Okay. If you guys pay 80 Rand, you can go to the beach, which you can go to for free anyway if you want. Okay. They'll give you free for you. It'll probably be like a small snowball or something. I don't know. Anyway, irrational numbers and real numbers. It's helpful to do a little recap before we get here.
It's for students, but it's also open to everyone on campus.
Yeah. Is that person here? Can they hear us? Okay. That's all going to be in the recording now. I should have thought about that. But anyway, okay. So irrational numbers and real numbers. You guys remember the basics? We went over natural numbers, whole numbers, integers, all that stuff. Yeah. Anyone wants a quick recap? Anybody wants a recap on that stuff? No. Okay. Perfect. Let's just go straight ahead to irrational numbers and real numbers. So irrational numbers rational numbers we know can be written as an integer over an integer. So irrational numbers are just the opposite. You cannot write them as integer over integer. Right? So it's just the opposite of a rational number. Okay, so there's some examples here. Square root of 2, for example, is irrational. And if you can check this in your calculators, there's no way to write this as integer over integer. Another way to check with things like this is if you take the square root of a number which is not a perfect square, it's irrational. Right? A perfect square are basically the natural numbers squared. Right? So 0 squared, 1 squared, 2 squared, whatever those are, it will be 1, 4, 9, and so on. Those are all perfect squares. Take the square root of a number which is not a perfect square, it's irrational. Okay, anyway, if you forget that, it's written here. Right? What I just said is written here. Pi is another example of an irrational number. Everyone knows the famous number pi. Right? Okay. All right, that's another example. And here's some, so we don't want to remember specific cases. We want a rule to tell us if something is rational or irrational. And the rule is given right here, this statement. So, I mean, the first one is whether it's integer over integer, right? That's the first check. If it's not clear by that check, then we look at this one here, which says, let me highlight some points here, highlight in red. If a number is terminating or repeating, then it's rational. If a number is non-terminating and non-repeating, it's irrational. Okay, so what do we mean terminating and repeating? Maybe I should give you guys some examples. When I say terminating, I mean a decimal example of terminating. Let me try and make some arrows to point to each thing here. Where's the normal blue? So terminating would be, for example, why does that? For example, a number like 1.35, right? It's a decimal, and afterwards, there's a finite number of digits afterward, right? So this is terminating. If it went on 3572, blah, blah, whatever, dot, 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 forever, then it's non-terminating. Right, so terminating, we can see clearly it stops here. So that's terminating. Non-terminating would be, for example, 1.573218, blah, blah, blah. It just carries on. It doesn't stop. Right? Am I losing anybody so far? Right? Straightforward stuff. Okay. Repeating would be something like, where's the pen now? Like a 1.3333 and goes on. Right? That's repeating. Repeating is, it's always assumed to be non-terminating. Yes.
You say it's 1.35 or 7.
35 or 7. Then it's terminating. If it doesn't continue after that, it's terminating.
How can you see if it's terminating?
If it's terminating, it stops somewhere. Right? If it's non-terminating, it goes on. On your calculator, it will just go on till the end of your space there. Then it's non-terminating. If it's 3 numbers, then definitely it's terminating because we can see the end. Right? If you can't see the end, it's non-terminating. Okay, right? That's a good question. Is that okay? But always remember, in the examples they give you, they will give you obvious examples. It won't be something like that goes to the end of your screen and you wonder, is that the end of the number or is it, you know, they'll give you obvious examples like this one here. That's obviously terminating. If it's non-terminating, they will give you obvious examples as well, right? Like 3.33 recurring, something like that. Okay, so where was I now? Non-repeating. Example of non-repeating is something like pi, right? It just goes on forever and you don't get, so something like pi, which is 3.1415, I think, I forget the rest, but it goes on and you don't see any pattern there, right? There's no repeating pattern. Okay, we'll look at a few examples to clarify all of this. So far, everyone good? Okay, perfect. All right. Now, this is a bit of an annoying thing to remember. Sometimes I forget which is which, but we can keep going back to it as we need to. Here are some examples. Okay, let's see if we can figure out whether they are terminating or repeating. I mean, sorry, whether they're rational or irrational. And we'll first do our first check, right? So, sorry, I'm studying. Okay. So let's look at it, for example, 0.25 or 1/4. Right? We're looking at obvious examples just to get the principle. Yes. This is the lecture notes which are based on the module map. Yeah. You can find these on ARC. Okay. All right. So it should be uploaded on ARC. If anyone has trouble getting it, just let me know. Okay. Anyway, as I was saying, we start with this obvious example here, 0.25 or 1/4. 1/4, it's clear this is integer over integer, right? That's clear. So we know that this is definitely rational because 1/4 tells us that. But suppose we didn't look at 1/4. Suppose we just looked at 0.25. By the criteria above, where does this fall? So let's see, 0.25. Is it terminating or repeating? Terminating, right? It satisfies one of these two criteria up here. There's an or between these two words, terminating or repeating. So if it's one of these, any one of these, then it's rational. So we met it here, the first one, terminating. So we can stop immediately and say, yes, this is therefore a rational number because it's terminating. So rational, yes, we will say terminating. I'll just say. Maybe I should move it up because we have another example at the bottom. So let's just put an arrow there to the other one here. Okay, again, they made it obvious for us by writing this as 13/10. We know that integer over integer. right? But 1.3 by the criteria above, let's see, I think the same reasoning, right? Is it terminating? It's terminating, right? So we don't need to check anything else. If it's terminating, we just say yes. And the same reasoning for both, terminating. Okay. 0.66, here they show us that it's not terminating. So it's going on forever. Again, because they've given us this 2/3, it's clear that it is integer over integer, so it is rational. But again, we just want to check by our method. So 0.66, continuing, the sixes continue. Let's see, is that terminating? Not. Is it repeating? Yes, right? So that's the reason why we say rational. So this, yes, because it is repeating. I'll just say R. Okay. We don't have to do all of these. Let me just do one more. This number right here, let's see. 3.242424 continuing. So let's see what this falls into. Is it terminating? No, right? It continues forever because they put a dot, 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 so we can see it's continuing. Is it repeating? Yes, right? It's repeating. It's not one number repeating, it's two, but we can spot the pattern. If you can spot the pattern, then it is repeating. So this one here is yes, because it's repeating. Okay. All right. This one at the bottom is clear. It's integer over integer. 321 over 99 is integer over integer, so that's clear. That's all we need to see there. So yes, I'll just say here integer over integer. Right? If you wanted to, you could convert that to a decimal and check with the criteria above if you wanted to do that. Okay. Pi, we know pi is not rational, right? That's clear. But let's check by the criteria above why it's not rational. So I'm going to say no here. Pi, is it terminating? Not terminating, right? Is it repeating? No repeating pattern in pi. It's just continuously unknown numbers. Is it non-terminating and non-repeating? Both of those things together. It must be both of these together to be irrational. So it is non-terminating and non-repeating. So I'll just say non-terminating, non-repeating. Because there's a video here, you guys will know what I said when I wrote these things down, in case anyone misses the words. And the last one, you guys can check that at home. Okay, oh, and the solutions are here as well for us to check at some point. And here, I'll leave this up for a few seconds. This is just a summary of all the different number types we learned and how they kind of, the sense of them put into one another. Okay, so in case we haven't mentioned it yet, everything that we covered so far are real numbers. Everything. All the sets, the irrational numbers, rational numbers, our whole numbers, integers, natural numbers, all of these are real numbers. I think I said real numbers twice there. Everything that we've learned, everything within all of these circles are all real numbers. Right? I think there's a better summary somewhere down. There's it here. Okay. So it seems like an odd thing to define real numbers if it's just everything else. But the reason we define real numbers is because we will learn about something new, which some of you might have seen before, called complex numbers, right? That comes later on. And that has to do with mathematical ways to deal with weird numbers like square root of -1. Anyone heard of complex numbers before? Dealt with complex numbers. Heard about it a little bit. Okay. All right, things get strange there. Gets a bit strange. This is where you get into like the realm of quantum physics and Schrodinger's wave equation. Interesting stuff. All comes in the realm of complex numbers, which are technically not found on the number line, but they seem to exist in nature, which is a weird thing. Right? But anyway, unfortunately, we can't get too much into the physics of these things. We just do the boring maths, which is okay. Okay, so now, can I give you guys some time to try a few examples here? See, someone said no. I feel your pain, guys. Trust me, I do. Okay, the first one we can, okay, let's see. Just do the first, just do three. There's three here, right? We can do three examples. Just try them out. Few minutes. Tell me now. Okay, guys, for the first one, what did you guess? Rational or irrational? Yeah, rational. You think rational? Put your hands up. But anyone for irrational? Okay, most people say rational. So the criteria, this one here is, it's a terminating number, right? If it's terminating, that means rational. So just go back and check the criteria if you get confused. It's okay. We always go back and check. Where is the thing? It's right up here. So terminating, right? It's only 2 decimal places after the decimal. So it's definitely terminating, and that's all we need to know that it's rational. Okay, so this one here is rational. Let's say R for rational. And these are not too difficult. Let's just look at the second one together. What sets of numbers does 32 belong to? So I'll take it from the top. Is this a whole number? It is a whole number, right? So we have to remember the symbols now. W, I think, is for whole numbers. It's weird W. Is it a natural number? Yes, got a few yeses. Right. Natural number, hands up for natural number if you think natural number. Okay, perfect. Correct. It is a natural number. Natural number. Is it an integer? Got some no's. Yes, some no's, some yeses. Okay, so remember, this is just a matter of definition, right? Thank you. Remember, the integers are just the negative and positive version of your natural numbers. So 32 is a part of that set, right? So 0, 1, 2, 3 going on, -1, -2, -3 going on that way. Those are all integers, right? So integer, the symbol is Z. I'll just write the Z here. After integer was what? Rational, I think. Yeah. Is it a rational number? Yes. We got some votes for yes. Okay. Is it integer over integer? Right. 32 over 1, right? So that's the trick here. If you write 32 as 32 over 1, which is technically the same thing, it is integer over integer, right? So that's definitely rational. Is it irrational? Can't be, right? If it's rational, it can't be irrational. And is it real? Must be real, right? If all of these are real. So what's the symbol for real? If R is rational, what's real? I'm asking because I don't remember. Does anyone know? I'm just going to write here real in words. Okay. When you guys write these, just to be safe, write in words. If you're not sure of symbols, just write in words. It's always safer. I'm just writing in symbols to be quick here in the lectures. Okay. Does anyone know, though, the symbol for real numbers was, it's the same thing. Both the R's. Okay. That's a bit, that's not ideal. Okay. Anyway. Hey, what sets of numbers does 382.3 recurring belong to? So firstly, if you haven't seen this, this is basically just 332.333, and the 3 goes on forever. Right, 3 recurring. Okay, so is this a whole number? Not a whole number. Is it a natural number? Not natural. Integer? Not an integer. Rational number? Yes, but the criteria rational because it's repeating, right? So because of that, we say rational, and then it must be real as well, right? Everything we've dealt with is real. Okay, and you guys can check the last one at home. Let's not spend too much time on these things. Exponents and square roots. Okay, so again, if you look at the module manual, you'll see there's a whole long story on these things, right? So I'm just trying to compress it here in the notes, is that an exponent and a square root are basically just opposite operations of one another. Let's get some notation right firstly. So, right, yeah. A to the power n is the basic notation we use for exponents, where A represents what we call the base and n is what we call the exponent. Right, just two words we have to remember. And we'll look at some examples at some point. Did I show? Yeah, here we go. Okay. So again, for those who don't know this, an exponent is just a way of representing repeated multiplication. Right? That's all we're trying to say here. So for example, if I had 3 to the power 5, it means 3 multiplied by itself 5 times. So this is just 3 times 3 times 3 times 3 times 3. Right? And there's two more examples above with 7s, which you can look at. Okay, so there's an example down here. Quickly find the value of 4 squared. I'm not sure why that's an example, but it's here for some reason. The same as 4 times 4, 2 times, right, which is 16. So just very basic stuff to get us used to the basics. Okay, and now a square root, roots in general, but we're talking about square roots here. Roots in general are opposite operations to exponents. So for example, well, there's an example right here. 2 squared gives you 4. To take the 4 back to a 2, you take a square root, right? So it just undoes what an exponent does. The exponent turns a 2 into a 4. The root turns a 4 back into a 2. Just opposites. Okay. And for those who will look at this and say, technically, square root 4 is plus minus 2. That's correct. But for some reason in this module, I think we're using, it's like an American syllabus or something, where we look at what's called the principal square root, which is only the positive version of it. Right? I look at this thing, it makes me quite uncomfortable, but that's what they do here. And again, I don't set your exams and your tests and stuff, so I have to follow the syllabus as it is. So we always just take the positive version of the roots. But later we'll see they get fussy and they start looking at negatives as well. So it's like a context dependent thing, I think. But again, when there's any ambiguity, when I'm marking, I always give you guys the benefit of the doubt and give you extra marks rather than less. So if you're not sure about that, don't stress. Okay, now just more definitions. Radical sign, if you haven't heard of the word radical sign before, it's just this thing here, the square root on top of the 4. This symbol here is called a radical sign. Just a word to remember. Yeah. Okay, so just remember that word for multiple choice purposes. Division. It looks like division. I know it actually does look like division. That's a good point. So this looks like division, but it's not. I guess maybe because of the little thing here that differentiates it. Or division has like a. Okay, I don't know. But just so you guys know, we don't do division like that in this module. So whenever you see this, it's always a root. Okay, all right. But that's, I didn't even think about that. That's a good point. Okay, anyway, what other interesting stuff can we do? Perfect square, I'm going to define these things just because it's highlighted, so we need to define them. A perfect square, as I just mentioned, is just a natural number squared. The result is called a perfect square. So there's a table of all the, not all of them, but some perfect squares. Okay, is it clear to you guys what I mean here? Perfect square, right? Straightforward. Okay, and we have some examples here. I like to skip all of these, but I don't think I can. Well, sorry. I think we should do these just because this is going to be in the video for anyone who might be confused and afraid to say anything. So let's do a few of these. Okay. Just bore myself. Let me do every second one. We'll see. If we need to do anything in between, you guys can let me know. I'll start with the first one. 14 plus 28 divided by 2 squared. Do you guys want a few minutes to try it before I do it? Extra. Okay, we can do it together if you guys want. Okay, just watch me. I'll pretend I know absolutely nothing. You guys tell me what to do, right? So it's like you guys are doing it and I'm just watching. Okay, so what's the first step I need to do here? 2 squared, perfect. 14 plus 28 plus 2 squared is what? Oh, sorry, divided by. Okay, I'll say I gave the answer away anyway. It's okay. Okay, divided by. Okay, now what do I do? Division, right? 14 plus 4, I have to do this in my head, 4, 12, 7, thank you. Okay, then there's just one thing left to do, right? Just adding. So 7, 8, 9, 10, 11, so it's going to be 21. Okay, all right. Every second one. So anyone wants to see me do the second one here? Yes, okay, so let's do it. Let's do it. Again, that's what I like, guys. If you tell me, then I know we can do them. I don't like to skip things if we're not sure. So first thing we do here is work within the brackets, right? Within the brackets, we got a 4 plus 3. Okay, thank you. So we got a 7 squared plus, let me just write it step by step, just so everyone can see the steps of word mass. Okay, so 7 squared gives me what? 49. 8 times 4 gives me 32, right? I don't know why I wrote it like that. Let's write that better. 32. Okay, and can someone add these for me? Let's see. 40, 50, 70, 70, 80, 81, right? Okay. All right. Very basic stuff, but still nice to get used to it if you haven't seen it in a while. Okay. These are two slightly distinct examples. So let me just do both to make sure we don't mix these up, because people mix them up sometimes. There's an evaluation that says find 5x cubed if x is equal to 4. So you just substitute x is equal to 4 and you get 5 times 4 cubed, which is 5 times 64. 64, which is 320, I think. Right. Okay, again, just double check my quick maths because it goes off very often. Okay, please don't, but thank you. Okay, and very quickly, I'll make the point with this next one is that I'm not going to do the whole thing. If you have 5x and the cubed is on the outside, you substitute the value into the bracket. So 5 times 4 and the cubed is on the outside. Right, so that becomes 20 on the inside with the cubed on the outside. And 20 cubed is, I don't know, anyone knows? 2,000. 8,000, thank you. 8,000, yeah, that seems right. Okay. And the last one, I'll leave you guys to try that at home, where I just make a note here, be careful that you have a negative sign in front of the 4, so take that into account when you substitute in. Yeah, so I'll just get it started. It'll be -4 cubed, and then you guys can work it out from there. Straightforward stuff. Yeah, that's correct. Okay. Let's see how's our time. 10:34. Still, we're not there yet for a break, unfortunately. 10:34. Break at 10:05, right? Okay. We still surviving? Okay. I think I also am. Exponents of 0 and 1. There's a diagram here for some reason. Okay. Okay, so exponents of 0 and 1, I think most people know sort of by definition what these things are. Like if I told you anything, let's say 2, okay, let me use a 10 since they're using tens. 10 to the power 0, you guys know what that is? 1, right? And 10 to the power 1, 10. So we know these things sort of by definition. But now can we prove that these things are true? Okay. 10 to the power 1, let's think about what that means. Okay, that's not too bad. Because you know exponents, for example, 10 squared is telling us to multiply 10 by itself 2 times. Right? Okay, guys in the back, just a little bit quieter, please. I feel like I'm shouting over you. Thank you. You guys can still talk, but just a little quieter. All right. So as I was saying, 10 squared means 10 times 10, 2 times. So we're multiplying 10 by itself 2 times. 10 cubed is 10 multiplied by itself 3 times. So 10 to the 1, kind of intuitive. It's 10 not really multiplied by itself, but 10 by itself one time. So 10 to the 1 is not so bad. We can make intuitive sense of that one. What about 10 to the 0 though? Does that make any kind of intuitive sense? What's the 10 multiplied by itself 0 times? I'm not sure. So 10 to the power 0 is 1. We know that by definition, right? Can anyone make intuitive sense of that? It's not so easy. It's not so easy. So the way that we arrive at this result is by just following a pattern. Let's look at the pattern here. So if you have 10 to the 5, for example, we start at the top. 10 to the 5 is just 10 multiplied by itself, right? 5 times, right? So that's clear. Sorry. Okay. And we're just following a pattern. 10 to the 4 is the same idea, 10 multiplied by itself 4 times, right? So to get from 5 to 4, what did we do? Anyone? We divided by 10, right? So essentially dividing by 10 to get here. And every step of the way, we keep on dividing by 10, right? To get to each one, we keep on doing the same thing until we get to 10 to the 1. Now to get from 10 to the 1 to 10 to the 0, should we not just do the same thing? Just divide by 10 again, right? So this will be 10 divided by 10, which is 1. Right? So that's where the result comes from. It doesn't come from really an intuitive understanding. It comes from just following a pattern. Okay. All right. Okay, so is that okay for everybody? All right. So now using the same logic, okay, we'll come back to this in a moment. Let's look at negative exponents first. Using the same logic, let's see what happens if exponents become negative. So by the same logic, we know 10 to the 0 is 1. If we keep on dividing by 10, from 0, we go to 10 to the minus 1. Get 1 over 10, right? So 10 to the minus 1 is 1 over 10. What about 10 to the minus 2? 1 over 100, right? Or 1 over 10 squared. Right, so from this, we get the result. The famous result that you might know is that 10, let me not say 10, any base, a to the power negative n is the same as 1 over a to the positive n. Right, so we've just proven this result here. Okay, so if you don't want to know the proof, don't worry, just memorize the result. The result is important. That's what we will be using. And we skipped some stuff here for some reason. Okay. Okay, so yeah, maybe we should look at this number 0 over 0, 0 to the power 0. Let's see, what do you guys think this is? You might have read it already. 1, right? 1 is a perfectly reasonable guess. Anyone thinks anything else? Not possible, right? Yeah. So yeah, so let's think about this. Let's try and approach it logically, right? We know that something is wrong here. Something is clearly wrong here. Let's see what happened up here. 10 to the power 0 was 1, right? So by that logic, 0 to the power 0 would be 1. If we know something to the power 0 is 1, then this must also be true, right? But also, 0 to the power anything, let's say 2, for example, what does that give us? 0, right? It's 0 times itself 2 times. So by that logic, if 0 to the power anything is 0, then 0 to the power 0 should also be 0. Right? So we got 2 results for the same thing, which is a bit of a problem. Right? And luckily, we don't have to deal with this because we say that this object is undefined because it does weird things. So we just avoid it. When we see it, we walk the other way, right? We don't deal with it. I think in more advanced mathematics, people try doing strange things with these objects, but we're not going to worry about that. We just ignore it as much as we can. Okay, and for some reason, we have an example here which looks trivial, but let's do it anyway for the purposes of the video. Evaluate 2x to the 0 if x is equal to 9. So 2x to the 0 just becomes 9 to the 0, which is just 2. Why is this thing keep smudging? Which is just 2 times 1, which is just 2. Anything to the 0 is just 1. Did I lose anyone along the way? Yes, okay. Okay. It's all right. Okay. Negative exponents. Let's see. How's our time? 10:41. You guys still surviving? 4 more minutes, we can manage. Okay. Negative exponents. So all the rules I've been telling you guys are summarized in these blue boxes here. This first one gives us the exponent rule for the negative exponent. So that's there. And now, in 4 minutes, can we do 4 examples? Okay, I don't want to rush too much because these are new rules we're learning. Let's see in 4 minutes if we can do at least 2 examples. The product rule for exponents, again, you guys would have probably seen this before. Basically says if you have the same base, 2 exponents here, it's x to the a times x to the b. X is the common base, then the result is x to the a plus b. Just shows you how to combine expressions with multiplication for exponents with the same base. So using that rule, it's best to learn with an example. This example down here, simplify a cubed times a to the 7 is just a to the 3 plus 7, which is a 7, 8, 9, 10. Let's do that better, 10. Okay, and now applying the same logic to the one on the right. Here it's just showing us if you have coefficients, you just move them to one side. You don't have to stress about them. So this becomes 5 times 7 on one side and a to the 4 times a to the 6 on the other side. Okay, 5 times 7 is 35. Correct me if I make mistakes, please. A to the 4 plus 6. That is 35. A to the 10. Sorry, 12, right? No, it's 10. It's 10. It's fine. Okay. It's fine. Okay. 8.2. We did 2 examples in 2 minutes virtually. I thought we'd be done by now, but we're not. Okay, you guys, anyone needs any further explanation on these 2 examples? Okay, again, guys, don't be afraid. Anybody at all? Oh, good. Okay. So let's see if we can do at least one more example before the break. The power rule is the next rule which tells you how to deal with an exponent raised to a power. So for example, x to the power a, all in brackets, raised to the power b, becomes x to the a times b. People often confuse this with the rule we just learned before. So just be careful to make sure you know the distinction between these two. So for example, guys in the back, please a little bit quieter. Thank you. So here, for example, there's a 6 in front. We just ignore the 6. It doesn't do anything. 6, and then we have c to the 4 times 2, because the 2 is on the outside of a bracket, raised to the power. So this becomes 6c to the power 8. Okay. And now this last example is a combination of both the rules we've learned. You guys want to take a minute to try that one. Like 30 seconds. It shouldn't take too long. Just with the 2 rules, try this last example. Okay, guys, it's 10:45. We can take your break and I'll show you guys the solution when we come back.